Okay, good morning, everyone. And so let me just, before I continue, recall some notations. So we had S, a smooth closed surface, and then X was a compact Riemann surface. G was a simple or semi-simple, generally complexly group, and GR a real form of G. HR was a maximal compact, and then we have the Cartan decomposition here, and I complexify the group, the maximal compact, I get generally a reductive group H, and then complexify M, the orthogonal part to the Cartan decomposition with the killing form, and I have the isotropy representation. These are the Lie theoretic ingredients to remember define the notion of so isotropy representation to define the notion of GR Higgs bundle over X, which is simply as a pair E phi, where E is a H principal bundle, a holomorphic bundle, and phi is a holomorphic section of the associated bundle to E via these isotropy representations. So it takes values in this vector bundle, tends to the canonical line bundle of the Riemann surface. And so just recall that by M XG, we meant the moduli space of polyastable, whatever, semi-stable GR Higgs bundles. And so remember that we have the moduli space of representations that I denoted by RSGR. This is just the reductive homomorphisms from the fundamental group of S to GR, conjugacy classes, right? And the non-abelian Hodge correspondence establish a homeomorphism of this moduli space of representations with the moduli space of homeomorphism of Higgs bundles for this real group. That could be complex, remember. And then the other, so I'm just trying to summarize what we saw yesterday. There was the situation when GR was split real form. So then in this situation, so we have the hitching map that goes from the moduli space for this split real group to the hitching base, which is just a direct sum of holomorphic sections of various powers of the canonical bundle, let's say Mi, right, certain I. And Hitching constructed a section of this, and that defined components. So Hitching image are the so-called Hitching components. And so this generalizes the Teichmuller space precisely when the group is SL2R, and in that situation one gets the quadratic differential. So and an important point was that these components had properties similar to the Teichmuller space in the sense that they consisted entirely of discrete and faithful representations. And so the goal of my talks was to exhibit components, what we call now generally higher Teichmuller components that enjoy those properties, loosely speaking. Sorry?
This notation is the MFG or MFG?
Oh, sorry. Yes. GR. This is for the group GR. Thank you.
Are you done? So what? H not XK, my index I runs.
So the index is, from 1 to L, whatever. Yeah. So I will actually in the process I will come back to this. In fact. So So we started yesterday with, so there was one class of groups for which there was this sort of components. These were the split real groups. And I said there was another class of groups, these Hermitian groups, groups of Hermitian type. And I started telling you about them. But let me actually come back to that, because it's easy to forget. So let's now consider this class of groups that are forms of real forms of Hermitian type. So, and remember that that means that the symmetric space, GR mod HR, admits a complex structure which is compatible with the Riemannian structure that the symmetric space has. And in fact, this is a Kähler, right? This is a Kähler manifold. And that is, so for example, let's just consider, not for example, but just to simplify, let's suppose that GR is simple. And so in this situation, those groups are characterized by the fact that the Lie algebra HR, the Lie algebra of the maximal compact, is one-dimensional, and so it's really R. And so that defines precisely the complex structure. This element in the center, so defines the complex structure that one has here, and that complex structure defines the decomposition of the isotropy representation in MM, in M plus, and M minus. This is the 1-0 part of that complex structure. This is the 0-1 part. So I'll go a bit fast on this because I mentioned this yesterday, but I just wanted to. So just to know what we are talking about, to realize that these groups of Hermitian type, in the classical groups, these are the following 4 families here: the SUPQ, the real symplectic group, and then this non-compact dual of the orthogonal group. And because we want to have connected groups, I just take the connected component of SO to N. So these are, or finite covers of this are of Hermitian type, right? And then there are 2 exceptional real forms, one of E6 and another one of E7. And this is all, right? But this is all very some wonderful, fantastic world of these groups, and manifests in many areas of mathematics and physics. So a consequence from the point of view of Higgs bundles is that these the bundle where the Higgs field takes values decomposes in 2 irreducible representations. I mean, in two bundles, because this is this representation decomposes in 2 irreducible representations for the H. So this is M plus and N minus. And so this bundle decomposes as a direct sum of 2 bundles. And so the Higgs field has actually 2 components. We saw this already in the case of SL2R, right? And so that I call beta and gamma. And the other important fact is that similar to the case of SL2R, which is the simplest example of groups of this type, is the fact that the topological invariant associated to Higgs bundle, which is the topological invariant of the H bundle E, which is always an element in the fundamental group of H, happens to be an integer, right? So the fundamental group of H, okay, I must say that the fundamental group of H may have sometimes some torsion, and that, as a matter of fact, only happens in the families that I showed before in the case of SO to N, right? And in which there is a Z2, but there is always Z, right? The torsion-free part is always the integers, and so you can, the topological invariant is an integer, and this integer is what is known the Toledo invariant. Sometimes the Toledo invariant is actually some multiple. There is some normalization involved, which has to do with the geometry of the symmetric space, with the sectional curvature of the symmetric space. And but modulo that, the Toledo invariant is just that integer, which in the case of SL2R was the Euler class. Okay. And so, like in the case of SL2R, where we have the Milnor inequality, there is this Milnor-Wood inequality that gives a bound on this integer in terms of the rank of the symmetric space, or the rank of the real group, and the genus of the surface -1. And yeah, so this is proved by different methods, and yeah, I mentioned this yesterday. So we have this Milnor-Wood inequality. And the goal, I want to exhibit the existence of special components when this Toledo invariant is maximal, which in the case of SL2R was when the Euler class was maximal, and that led actually to the Teichmuller space, well, identified with the Fricke space. And we'll see that in this maximal situation, something happens as well, but not for all groups of Hermitian type. There is, now we have to enter a little bit into the geometry of the symmetric space to distinguish what are called of the symmetric spaces, those that are of tube type and those that are not of tube type. And so to explain that, let me now get into the, a little bit into the geometry of the symmetric space, and a very important fact that plays a crucial role, and this is in fact one of the reincarnations of these objects, is the fact that these symmetric spaces can be realized as bounded symmetric domains. And they can be realized as bounded symmetric domains for D, for example, in M+. It could be in M-, but let's choose M+. And this was shown by Cartan for the classical groups, and Harishchandra had the general picture, right, of how to do this. The precise map to go from this symmetric space to a bounded symmetric domain in this complex vector space. And so D, this symmetric domain, is called of tube type if it is biholomorphic to a tube over a cone. So this means basically that so a tube over a cone, it means that there is a real vector space, let's say a VR, a real vector space, and this is this plus I times a cone, where this cone is in VR, right? And so whenever your domain can be put biholomorphically like that, it is said to be of tube type. And the fundamental example to have in mind is precisely the case of SL2R, actually thought of as SU11, where the bounded symmetric domain is the Poincare disk. And of course, the Poincare disk is isomorphic to the upper half plane, right? And as we all learned when we learned one complex variable, right? And so we have the Poincare disk, and then we have the upper half plane. And this is indeed a tube over a cone, where actually the cone is particularly simple. The cone is simply this thing here, right? And so this is the vector space VR that I'm putting there is this, right? So this is the cone realization of the Poincare disk. And so this morphism, as we know, is realized by the Cayley map or Cayley transform or something, right? That we all learn in school. And so the tube type domains, okay, so are those that admit this kind of realization, that for which there is like an upper half plane, right? And so one characterization of when this is possible is given in terms of what is called the Shilov boundary of the symmetric domain. And so this Shilov boundary is just a part of the topological boundary, generally just a piece, not the whole boundary. I mean, for the case of the Poincare disk is the whole boundary, coincides with the boundary. But in general, it's just a subspace, and it's characterized by this fact that every continuous function on the closure, and which is holomorphic on the bounded domain, actually acquires this maximum in the Shilov boundary. That's what characterizes the Shilov boundary. And so the tube type condition in terms of the Shilov boundary is that is always true that the Shilov boundary is actually a homogeneous space, but which is compact. But when that homogeneous space is symmetric, then the thing is tube. And in fact, so when S is a compact symmetric space of the form, which is the compact group HR modulo some subgroup, right? Then the thing is of tube type, and in fact the cone is explicitly given by this non-compact dual symmetric space. So remember, when you study real forms of a complex group, there is one which is compact, one which is non-compact. There are many others that are non-compact. So this, but when you go to symmetric spaces, right, this sort of a symmetry is reestablished in the sense that for every compact symmetric space is a non-compact dual, right? And so in this case, so this is a compact symmetric space for actually the group HR, and so there is always this non-compact group. Both of them are actually real forms of H, right? And this is the non-compact dual. So this is the cone, right? And so which groups are actually of tube type? For example, the symplectic real group and SO2N are always of tube type. I mean, the symmetric spaces, right, corresponding to that. Now, for SUPQ is of tube type if and only if P and Q are equal. Otherwise, is non-tube. And then the SO star 2N is of tube type when N is even. In the odd case, when N is odd, then it's not of tube type. And of the two exceptional domains, this one, the E7 one is of tube type, and the E6 one is not of tube type. And but what is important also is that every non-tube type admits always a tube type subdomain. So for certain aspects, the whole theory can be reduced to the tube situation, okay? And it's also nice to, for example, for the SP2NR, this, the symmetric space for SP2NR is SP2NR mod UN, right? And the tube realization is the Siegel upper half plane, right? Which plays such an important role in many, in the theory of abelian varieties and so many other things, complex structures and so on. That in fact parameterizes complex structures compatible with a symplectic form, right? And anyway, now, any question on this? So, what I want to now show is that when the group is of Hermitian type and of tube type is when you have these higher Teichmuller components, right? And then here is a whole lot, which is now we fix the Toledo invariant to be maximal. Remember that meant that D was this bound here, and we call M maximal this moduli space for this value here. And so here's the key thing. The key thing is that this moduli space can be realized now, be seen to be by holomorphic to another moduli space. This other moduli space is a moduli space of, let me say, Higgs bundles, right? But instead of the usual twisting by K, remember we have a twisting by K in the theory of Higgs bundles, the twisting here is by K squared, right? So they are, properly speaking, not Higgs bundles, right? But but Higgs pairs of some sort. It's just twisted by K squared. And now the group here is precisely the non-compact dual of the maximal compact of GR, right? That was determined by the Shilov boundary, okay? And so the statement is that the moduli space of maximal Higgs bundles is isomorphic as a projective complex quasi-projective variety to the moduli space of K squared twisted H star R Higgs bundles. And this was proved for the classical groups in works with Bradlow and Gotten, and then for this particular group with Ignacy Mundet and Peter Gotten. And the general proof that doesn't use classification, and in particular then includes the exceptional groups, was in my work with Guichard and Rubio, right? And So one consequence of this, we call this Cayley correspondence. And we actually chose this name, of course, by analogy with this Cayley map in this more general context. But I think we have never been so fortunate of finding a name more appropriate than in this occasion, because this that was, in a sense, kind of analogy turns out to be strictly the right name from many points of view, right? And as I will explain later on. And so one particular thing that this correspondence shows is that the components. Yeah, so in particular, sorry, I should have put max here. The components of these maximal Toledo Higgs bundles are not distinguished by the usual topological invariant, meaning the usual topological invariant is the Toledo invariant. So it so happens that for this maximal Toledo invariant, there are other topological invariants, which are clear. The fact is that now from this picture, you realize that the structure group, the new structure group here, gives you new topological invariance for this, right? For the bundle whose structure group is H star R. And in fact, the maximal compact of H star R is H prime R. And so the fundamental group, in particular, of H prime R gives you new invariance. And moreover, in fact, typically, and in all the cases happens like this group that we have here is non-connected. So as I was saying yesterday, even if you start with a semi-simple group, which is, or simple in this case, which is connected, you end up in a theory where the group that you have here is generally a reductive group, right? And in fact, non-connected. And so there are new invariants, and for example, if you consider the case of the Siegel upper half, so the group of the real symplectic group, in that situation, the maximal compact of this is UN, and the dual non-compact is GLNR. So you have now, you're dealing with GLNR bundles, and so the Stiefel-Whitney classes of, so the maximal compact of GLNR is ON, which is disconnected, right? And now the Stiefel-Whitney classes of that give you new invariants. Right? And so that exhibits the, for example, it's actually fun to think again about the case of SL2R, and SL2R in this language is SP2R, so n equals 1, right? And so then you're dealing with a GL1R Higgs bundles. The maximal compact is O1, right? And so this is, no, what do I, yeah. So this is where you see the square roots of the trivial bundle appearing. So what are orthogonal structures on a line bundle? These are precisely square roots of the trivial bundle, right? And so these are the 2 to the 2G things that we saw appearing, right, in the Higgs bundle, in the Hitching picture, right? So in a sense, the first to have encounter, as usual, this kind of Cayley correspondence was Hitching, right, for the case of SL2R, right? Except that in that case, it's really a very minute kind of group, but it's there, right? Now, from the work of Burger, Yotzi, and Labourie, it turns out that they find that, like the case of the Hitching components for the split real forms, these are also, these components are consisting entirely of discrete and faithful representations. And also another important property that is shared with the Hitching components is that the mapping class group acts properly on this, right? Like in the case of Teichmuller space, usual Teichmuller space, the mapping class group acts properly and you get the Riemann's moduli space, right? So that's an important feature of this generalized component. So these all share these properties. And so in that sense, we haven't properly yet defined what's a higher Teichmuller component. In fact, part of this talk is to go to get to that, right? But if you think of this as components that are consisting of representations that are discrete and faithful and that are not fully determined by the usual topological invariance, they qualify, right? And also you can add to that the mapping class group acts properly, discontinuously, but well, then you are there, right? So these are higher Teichmuller components. And now, as I was saying yesterday, it was believed for a long time that the two classes of groups for which these things existed, so split and Hermitian, there were only these two classes of groups, and it was kind of, well, it wasn't really a total surprise, but it was at some point it was a surprise that there was indeed at least one more class that was detected to have special components of this kind. And so this came in the study of the group SOPQ, right? And SOPQ, I mean, you can take also the connected component if you want, but we can also now consider the whole case of SOPQ disconnected group, and we can study that as well. And so, and the whole theory applies. And building upon the work of my former student, Marta Aparicio, who worked in her thesis, this problem, where we really thought that the answer was going to be straightforward in the sense that the usual topological invariants were going to determine the connected components. But using the Morse theory approach that we have always used to count components, and that was started by Hitching, it was realized that, I mean, you have to identify minima of the Hitching function, and she found more minima than you would expect. And so you wouldn't know if those minima were in the closure of some components or what, so it was inconclusive, right? But there was already the suspicion that maybe there were components that were not detected by the topological invariance. And this is what turned out to be 3 years later. And so let me just say that an SOPQ Higgs bundle is a triple. If again remember that in the context of classical groups, we think of these things as vector bundles, right? So it's two vector bundles, V and W, equipped each one with an orthogonal structure, and the determinant of W is isomorphic to the determinant of V, and there is a Higgs field which goes from W to V tensor K. So these are the objects, and there's a moduli space and so on and so forth. And now the topological invariance. So let's consider the case P bigger than 2, because first of all, if P is equal to 2, we fall into the class of Hermitian groups, right, that we have studied somehow, right? And P equals to 1 is particularly simple. This is the one case actually that we solved with Marta, and we wrote a paper about it, and counting components and so on. And so if P is bigger than 2, then you have that orthogonal bundles are classified by first and second Stiefel-Whitney class, right, in here. And so we have two orthogonal bundles, okay? But they are linked by the determinant condition. So the first Stiefel-Whitney class of V and W coincide. And so the only, so we have just to consider the first Stiefel-Whitney class of V, which is equal to W, and then the second Stiefel-Whitney class of V and W. So the invariants are A, B, C living in these groups here, right? We have 2 to the 2g possible values, of course, for the first Stiefel-Whitney class, right? And so these are the invariants. And so one thing that one proves quite so you can separate the moduli space. The first is to separate in this subvarieties when you fix these 3 invariants, okay? And so the first result that we proved is that if you fix these values, I mean, this condition on Q is irrelevant in the sense that you can reverse the role of P and Q, right? So that's why we choose this. And so the first thing that we show is that if you fix this topological invariant, there is indeed this space has a non-empty connected component, which is just determined by the topological invariance. And in fact, that component can be are Higgs bundles that can be deformed to a Higgs bundle where the Higgs field is 0. So they correspond to, from the point of view of representations that factor through the compact subgroup of SOPQ, right? And so we call this M-top. These are these obvious components that we prove that exist. And you prove they exist thanks to actually the results of Ramanujan, right? That identifies them as a moduli space. I mean, the minima in the Morse theory picture consists of the bundles, right? With actually bundles whose structure group is S of OP cross UQ, right? And so those exist, and so you have non-empty component and it's connected, right? One proves. Now, our main result is to showing that there are other components that we call exotic. I don't like these names very much, although they are now in print, because after a while they are no longer exotic. But anyway, so we call it exotic. Yeah. So and how do they manifest? So they manifest again similarly to the Hermitian case as a sort of Cayley correspondence. And so what we prove is that for each choice now of this, now you just have two invariants, A and C, right? Then you can identify inside this moduli space components that do not coincide, are disjoint with the topological ones, and that are isomorphic to, again, to a moduli space of Higgs bundles for a twisted line bundle that is no longer the canonical bundle. And in this case, in fact, you have that there is a moduli space of KP twisted Higgs bundles for this group here, SO1 Q minus P plus 1. And the reason you have just two invariants is because there is those are the invariants that classify these Higgs bundles. There is nothing more. And then you have sort of something similar to the hitching base, right? These holomorphic sections of these different powers of the canonical bundle, right? Now, so we actually we actually constructed a map from this space to the moduli space of SOPQ Higgs bundles and showed that that was open and closed and injective and so on. And so they consist of connected components. And we also showed that the elements here cannot be deformed to something whose Higgs field is 0. So they are disjoint from the other ones, right? They are disjoint to the topological components. And so now, it's still a conjecture that these exotic components are higher Teichmuller components. I.e. that they consist entirely of discrete and faithful representations. Still not known, except that you will, I will tell you that it is almost clear, and I will make this precise. So it's depending on a more general statement that I will make, right? And so the evidence, one evidence for this exotic components being higher Teichmuller spaces came from another front, okay, from the Morse theoretic approach. Yeah, so there was a suspicion there were other components. Here, after many years and hard work, we proved that there are these components. But there was another development that was very beautiful and very crucial, is that the work of Guichard and Wienhard that develop a notion of positivity for representations into some groups that admit themselves a notion of positivity. And there have been for many years, for real groups, certain notions of positivity, for example, for SLNR, and then Lustig introduce with, I don't know his motivation, but some notion of positivity for split real groups. And also for the Hermitian case, there were some notions of positivity. So what Guichard and Wienhard have done is to unify all this and generalize this notion of positivity for groups, for these groups. And then with that notion allows the definition of positive representation. So I'll come to that. But the fact is that if you look at the groups that admit this notion of positivity, here you find split groups, Hermitian groups, of tube type, so yeah. And then there is SOPQ, right? And so these are the only classical groups admitting positive structures, right? Or coverings of them, right? I mean, of SOPQ. Yeah, so groups locally isomorphic to SOPQ. And so to explain, let me now explain a little bit about this notion of positive representation, and be kind to me because this is not my approach, and so my expertise on it is quite limited, but I hope to convey some of the ideas. So before I get to the notion of positive representation, so the notion of positive representation is a refinement of the notion of Anosov representation. And so Anosov representation, that notion was introduced by Labourie and is a crucial notion, not just in this context, but in other contexts. So that notion of Anosov representation is built upon, okay, for a real group, and then you choose a parabolic subgroup. You have a parabolic, and then you have the Levy subgroup here of P, the Levy factor, and in here there is a homogeneous space of GR mod L, which is the unique open orbit in the product of these two Flack varieties that are consisting of pairs that are transverse, called transverse, right? Okay, let's keep that for a moment. And now, so there is the so-called the Gromov boundary at infinity of the fundamental group, right? Which in this case is realized actually as in fact, is the boundary of the Poincaré disk, can be identified with the boundary of the Poincaré disk. So is really a circle, right? And in all our cases, and so the so a representation is P Anosov. So this depends on the parabolic. It's a notion depending on P. If there is a unique continuous boundary map from the boundary at infinity of the fundamental group into this Flack variety, GR mod P, this continuous map must satisfy certain equivariance condition for the action of pi1 of S, and some transversality condition, and some dynamics properties. I'm really avoiding all this mostly by incompetence. But the important fact to retain is that so there is this map from the circle to this Flack variety, to generalized Flack variety, GR mod P, and this map is called the P Anosov boundary curve, right? And so yeah, so that's one thing. Now, so these representations, as I said, introduced by Labourie and have many interesting geometric and dynamical properties. And one thing which is, I mean, very nice is this Anosov representations. Let's say here Anosov representations are actually discrete, right? So it's a subclass of discrete representations, and this is an open subset of the space of representations, right? But is not closed. For a while it was believed maybe it was closed, and then this is what is the condition you're looking for. And say higher Teichmuller has been Anosov, right? But it was clearly quite soon actually shown that that was not true, and because this is not a closed condition, and so you cannot define components like that, right? And but And the thing that somehow misled a little bit to believe that was the fact that both for the Hitching representations and for the maximal Toledo representations, they actually were, this condition was enough, and this was counting, so this was giving components, if you want. But it was also observed, and it had been observed for the case of the split groups by Labourie and also by Fock and Goncharov, who, by the way, are responsible for the name of higher Teichmuller components or spaces. They coined that name. That there were some additional condition that those representations, that the Hitching representations had, some notion of positivity. That was a close condition, and the same was observed by Burger, Yossi, and Wienhard for the maximal representations. So that was obviously a hint for these people to look for a generalization of this. And so, so as I say, Guichard and Wienhard unified this notion of positivity that was, Lustig notion for split groups, and this other notion that had to do with causality and things for groups of Hermitian type and tube type. And so, again, this notion of positivity is not a positivity for a real group. It's a positivity for a real group equipped with a parabolic subgroup, right? And somehow the main ingredients is that you have the levy of this parabolic and you have the unipotent subgroup. And if you have such a pair and you can manage, so in the unipotent group, to find a semi-group of positive elements. There is a way of doing that, right? I mean, there are some ways of doing that for certain groups. And that semi-group is what is going to allow you to define a notion of positively oriented triples of pairwise transverse points here. Remember that in GR mod P cross GR mod P, there were these transverse things. And so if you have a triple of 3 elements there that are just 2 by 2, transverse, right? So this notion of positivity that, just keep in mind, they allow you to define some notion of being positive for this triple, right? Like in the circle, yeah, we have 3 elements. We can clearly know what is the notion of positivity. So here is now, once you have that notion of positivity, that I'm not telling you how you find it, it's rather elaborate, but I could say in my original transparency I had more information, but I had to readjust my talk to the time, and so I cut it down. So, but here is the thing, that if this pair admits a positive structure, then P Anosov representation, you have to start with an Anosov representation in order to have this boundary map, remember? So this Anosov representation is positive if this boundary curve sends positively oriented triples in the circle to positively oriented triples in this flag variety. So that is, once you have this notion of positivity, then you can make sense of this. So this was the refinement of positive representations. So as I say, so you have that positive representations are indeed here. So it's positive. Okay, and yeah, so this is still a conjecture, and the conjecture is that, okay, that positive representations, well, that they are open is easy. But now, yeah, that is known. So that is, I mean, already the Anosov were open, and this is also open here, right? So that is open. What is really the conjecture is that it's a closed condition. And it's still a conjecture, but I'll come to, I will add an extra condition that for which technically it's still a conjecture because there is no paper, but so this is Guichard-Labourie and Wienhard. They tell us, we believe them, that they have a proof. They are writing a long paper on this subject, and and if they have a proof, well, that's good news for us. I'll tell you why. But the conjecture still is that positive representations, P positive, because remember, this notion of positivity depends on a parabolic subgroup, is open and closed, and then that is the right condition. And so, and as I said before, the only classical groups admitting positive structures are split groups, Hermitian groups of tube type, and groups locally isomorphic to SOPQ. And so a tentative definition to hire Teichmuller would be to say that they are components consisting of positive Anosov representations. This would be the sort of the right definition, except that maybe we have to refine it a little bit more, right? But I'll come to that. So, and these components are not labeled by the primary topological invariance, right?
Positive means P positive for some P.
P positive for some P, yeah. So, and it's important because, as I'll show in a minute, I'll tell you in a minute when we discuss this, a particular group may admit several positive structures for different parabolic subgroups. So it's not just a question of the group, it's a question of the parabolic. So P positive, P is there, okay? I'm just avoiding two, yeah? Indeed. Now, something that we were able to show in the case of SOPQ is that our exotic components contained positive representations. And therefore, because of openness, they consist an open subset of positive representations. If we knew that the positive representations were closed, then these components would consist entirely of positive representations, but we don't know that yet, except that, so we don't know that yet. Now, what is also very interesting, so far I haven't told you if there was anything else, but the thing that is also interesting is that there are real forms. I told you what were the classical groups that admitted positive structures, but there are also exceptional groups. And these exceptional groups are real forms very clearly, so real forms of F4, E6, E7, and E8, and that are characterized by the fact that the restricted root system is of type F4. So those admit positive structures. And so therefore, you can see there is another world of higher Teichmuller components associated to these exceptional groups. Yeah? And so something that we have seen is that so from the point of view of dynamics and representations, there is this Anosov and this positivity and so on seem to be the right condition, right, that distinguish these components. But from the point of view of Higgs bundles, you know, Higgs bundles are not very good at detecting these properties of particular representations because the non-abelian Hodge correspondence is a transcendental correspondence and you don't know explicitly, right, what happens. So Higgs bundle techniques are very good at counting components, detecting the topology, and so on. But the phenomenon manifests the existence of these components manifests in another way. And the way that it seems to be manifesting is that what is it? So we saw that for a Hermitian group of tube type, there is a Cayley correspondence. For the maximal, and also we saw that for SOPQ, there was also this Cayley correspondence. So the thing is that the way in which this right properties of this special components manifests is in the existence of a Cayley correspondence. And this, in a sense, this Cayley, so there is meaning that you can identify some components of the moduli space with some other moduli space of twisted objects by powers of the canonical or and other things. And in something that we have loosely called Cayley correspondence, right? And in a sense, you can say that those components you detect, we could call them Cayley components because that's how we find them, right? And the conjecture is that these Cayley components are the same as the higher Teichmuller as being consisting of positive representations. And this is precisely what I want to give you now, the general picture of why this is so, and the fact that indeed this Cayley correspondence is a general phenomenon. And this general phenomenon manifests for real groups for which there are special nilpotent elements. And so these are groups for which there are what we call magical nilpotents. And again, this is one of those names that, you know, magical. I mean, but this is quite magical, actually. And okay, we heard before about wonderful compactifications, and now people use wonderful compactifications, so why not magical nilpotents? And this is a rather new concept. I mean, in Lie theory that it's quite surprising that hasn't materialized before, as far as we know. And we believe I mean, we see that it's an important concept and somehow may play a role in other things. But let me explain that a little bit. And so, as I said, so we will identify generally groups that admit this magical nilpotents, right? We'll give a classification, and we'll show that for those groups there is, in fact, a Cayley correspondence that, as I said, is very fortunate that we call it Cayley correspondence because it is really corresponding to what is called Cayley transformation in Lie theory, and which is related to which is realized by the Kostan-Sekiguchi. It's actually the Kostan-Sekiguchi correspondence, and so, as I say, this is a conjecture, but I really can almost remove the word conjecture and say theorem for something I will tell you in a minute. Okay, so here is what. Let me tell you then about nilpotents. So I want to consider actually a nilpotent. I want to start with a complex Lie algebra. Let's focus on the complex Lie algebra. And so recall that a nilpotent element is one for which the adjoint of this element is actually a nilpotent endomorphism of the Lie algebra, right? And we have inside the Lie algebra the cone of nilpotent elements. And the complex group, this is a complex, for the moment, all this is a complex story. So G acts on N by conjugation and has finitely many orbits. Now, there is one particular orbit, an open Des orbit, and nilpotents in this orbit are what are called principal nilpotents, right? So these are very well-known objects studied by Kostant and many other people, right? And so the Jacobson-Morozov theorem tells us that there is actually a bijection between these classes of nilpotents. Just take, of course, out the trivial one. There is a bijection between conjugacy classes of nilpotents with conjugacy classes of SL2 triples, so that if you start with this nilpotent element, you can complete it to a triple with F is another nilpotent, and then H is something semi-simple, and this expands an SL2 that is embedded in G, right? So these are SL2. So having conjugacy classes of nilpotents is the same as conjugacy classes of SL2s in the Lie algebra, right? This, with Ramanujan, we work a lot with this, and it's called sometimes abbreviated TDS for three-dimensional subalgebras. And Ramanujan's favorite joke was to talk about tedious. If you take the tedious and so on, yeah, it was not tedious at all, but that was, I cannot stop thinking of of that. So this is, as I say, so this of course had the right, the properties that an SL2 verify. So thinking of nilpotent elements and thinking of SL2s is the same thing, right? Conjugacy classes, right? And this is Jacobson-Morozov theorem. And so if you have this nilpotent element, then as I say, you have an inclusion of SL2C in G. And then this gives you an inclusion of PSL2C in G. Sometimes, depending on what is the center of G, you may have an inclusion of SL2 actually, right? But let me put generally, so it's SL2 or PSL2. And this actually, if you take the real part, the split real of that PSL2R goes to GR. So this is what you have. And therefore, you can see clearly that now, because of this inclusion here, right? If you take, you can see that from the point of view of representations. If you take a representation of the fundamental group of S into PSL2R, in particular, which is in the Teichmuller component, then this gives you something, a representation in the fundamental group in GR, right? And so you have the Teichmuller component always here, right? Once you have chosen an nilpotent, right? And whose image depends only on the conjugacy class of E, right? Because you have an SL2, SL2R, and then you get your Teichmuller inside of your moduli space. But most of the time, for most nilpotents, this image of the Teichmuller thing is in a connected component that contains Higgs bundles whose Higgs field is 0, so that you can deform to a representation that factors through the maximal compact most of the time. So most of the nilpotents from a certain point of view are bad if you are looking something that is discrete and faithful, right? But there is a class of nilpotents for which that doesn't happen, and this is the magic, right? As we call magical nilpotents, and for those, so far in this discussion, somehow, even though I have involved a real group, the notion of nilpotent is a nilpotent in the complex Lie algebra, right? Not in the, and so on. And so what happens is that those magical nilpotents do determine actually a canonical real form in a way that I will explain in a few minutes. And that happens only for the magical nilpotents. And so before I define you these notions of magicalness and so on, let me tell you what are the main results that we have, right? So these are joint work with Steve Bradlow, Brian Collier, Peter Gotten, and Andrea Oliveira, and we are finishing a paper on it. So these are just mathematically complete results, and we believe. And so here are the results. The first thing is a classification of this notion of magical nilpotents, right? And so the classification is that so a real form, GR, is such that its Lie algebra arises as the canonical real form of magical nilpotent of the complex Lie algebra, if and only if you are in this, you are split, you are Hermitian of tube type, you are locally isomorphic to SOPQ with these conditions here, or you are locally isomorphic to these real forms of E6, E7, E8, and F4, right? So this we classify. We define what is magical, and then we classify these magical triples or magical nilpotents. And as I already told you, this list coincides with the list of classification of groups admitting positive structure obtained by Guichard and Wienhard. And so a corollary is just by comparison of the classification is that a real form arises as a canonical real form of a magical nilpotent of G, if and only if it admits a positive structure. Now, as we were saying, the positive structure as well as the positive structure depends on a parabolic subgroup, and the magical property depends on a nilpotent element, right? And so it's clear that the nilpotent is related to the parabolic subgroup in a precise way, right? And it's also very interesting to observe that some groups, as one can see from the positivity, that some groups admit several, some real groups do manifest as canonical forms for various nilpotent elements. Or from the point of view of positivity, that, that some real groups admit several positive structures. So there are various parabolic subgroups that do appear. For example, first of all, for the split real forms, the parabolic is always the Borel, right? And so you always have the positivity that Lustig actually introduced was for the, now from this perspective, is P positivity for the Borel, right? And, but of course, if you think of the group sp2nr, that remember we said is both split and is also Hermitian of tube type, right? In fact, modulo local isomorphisms in small rank is the only group that has that classical group that has that property, right? In fact, is the only group that has that property. Then you see that sp2nr admits, in fact, two different positive structures. One is for the Borel, and the other is for actually another parabolic subgroup, which is a maximal parabolic subgroup. And in fact, the Flach variety, GR mod P, is the Shilov boundary, precisely, right? And so there is a hierarchy of these parabolics. The Borel is, of course, contained in the other, and so there is a relation, but there is a refinement of the thing. Another SOPQ, you see SOPQ, of course, if you have SOPP, it can be a split, or if you have SOPP plus 1, it can be a split. So it admits a positive structure of a magical nilpotent as a split group, right? And the Borel is the parabolic. But it also admits the one as a Hermitian when P is 2, right? And even if but I want to say that even in the split case, SOPP or SOPP plus 1, it admits another positivity structure. The parabolic subgroup is different to the Borel, right? And another interesting group that for which that phenomenon happens is for F4,4. This is the split real form of F4. So it has the Borel defining a positivity, but there is also another parabolic group defining a notion of positivity, right? So that's very interesting because, I mean, and this is all, right, that one has.
But do you say that when you have several magical nilpotents, that you also have a corresponding set of positive structures?
Yes, absolutely. I mean, there is a one-to-one correspondence. The classification, the classification of magical and the classification of positive is, they correspond. Except that we don't know yet how you get from a magical nilpotent to the notion of positivity. So it's just by comparison of the two classifications. The same elements emerge there. And of course, you can see the relation. In one case, you have a parabolic for the positivity. In the other one, you have a nilpotent element. But if you have the nilpotent, you complete it to an SL2 triple, right? And then you take the element H, right? In the triple, and then you can have find a grading of the algebra, and you take the parabolic part of that. That is how somehow they are related, right? Yeah. Okay, so this is. So let me continue with the results. So suppose then that. So this is. So what I said before is purely Lie theory, right? So here's where this notion of magical is a notion for nilpotent elements, and as I say, as a new concept that somehow has not been regarded before, as far as we know, and except, I'll see more, and now let's get to the components. So the one property is that If E is a magical nilpotent with corresponding canonical real form, remember that I said that magical nilpotent determines a real form, then if GR is a Lie group with Lie algebra GR, then there exists in the moduli space of, for that real group, a union of connected components determined by that nilpotent element that satisfy these properties. The Higgs bundles there have nowhere vanishing phi. So there's no phi never vanishes there. There's no element for which phi vanishes, right? So they don't factor through representations through the maximal convex subgroup. That's one property. The other one is that if you take now the image of the Teichmuller, right, that determined by the SL2R, so that is in here, and then that defines an open set consisting, there is, because of openness, I mean, we can prove that those are positive representations, right? And now, and here is the thing is that we give a explicit parametrization of these components in terms of a moduli space of twisted things for some number MC here, and some group that we call the Cayley Partner of GR. And then there are all these numbers here. So both these numbers that appear here, MJs, and the MC, as well as this group, the whole package is determined by E, by the magical nilpotent element, right, up to conjugacy class of E, right? And so, this is, what I would say is that we consider this space here and we construct a map to the moduli space of GR Higgs bundles, and we prove that is open and closed and that defines components, right, injective and so on.
Are the dimensions of those two pieces the same, for example?
Yeah. No, I mean, the dimension of, one thing you can count is indeed the dimension of this and the dimension of the moduli space.
No, but I mean the two pieces, the M thing and the product of the...
No, these are the whole, no, they are not the same. No, not at all. In fact, you can now, so the whole thing is actually, has the dimension of the moduli space of GR Higgs bundles, right? This thing here that you see as sections of some powers of the canonical bundle, as a matter of fact, you can think of them in a different way. You can think of them, of each piece here, as a moduli space of Higgs bundles, yeah, of, say, KMJ plus 1 twisted Higgs bundles for another group, which is the connected component of SO11. So you can actually say that this is a product of moduli spaces of twisted objects for other groups, right? But we wanted to present it like this because, first of all, so you can see that actually, I'm coming to that actually. I think I'm coming here. So we have, as I say, we construct a map from psi from this moduli space to the moduli space of GR Higgs bundles, and which is gives you these components, and you realize that we are recovering the three cases that we have already considered: the split thing, the Hermitian tube type, and the SOPQ. And you, as I say, this is a Cayley correspondence, right? And you may complain. I mean, you're complaining now.
Cayley correspondence, you define it for tube type.
Correct.
But there is more...
No. For Hermitian, so I defined the Cayley correspondence for Hermitian tube type. I also gave you for SOPQ, right, something that we call generalized Cayley correspondence, yeah? But I was hoping you would complain, what about the split? You didn't give me, well, I gave it to you, and I'll show it to you here. The hitching section is the Cayley correspondence. So the Hitchins section, right? You see, there are two extreme situations. One is the split groups for which this thing is trivial, there is nothing of this, and then you have just some of sections of powers of the canonical, right? And actually, let me put the next line, because this is exactly what I'm saying here, right? That if GR is a split, then the Cayley group is R plus, and then you have MI, I'm answering your question, what these powers, this MI here that you were asking in there, right, are precisely the exponents of the Lie algebra, right? And the degrees of the invariant polynomials, right? And so psi, in that case, is just the Hitchins section. So there, we never thought of the Hitchins section as something like this, as a Cayley. I was delighted to think, see, oh, that's an example of the Cayley correspondence. So there are two extreme situations. One is the Hitchins section, where this thing is, you don't have this, right, basically. Or, yeah, you have it, but it's just some sections of MC plus 1 that you can reabsorb here and remove this here, right? And so that's the thing. And then there was the other, the case of tube type, where this doesn't appear at all. This thing is absent. You only have this. And in fact, MC plus 1 is 2, right? And then in SOPQ, we found that there is a mixed situation, which is precisely closer to this, right? So, but this is the general picture, right? You always have like a mixed situation, which is kind of a mix of a Hitchins section somehow and some moduli space for another group, is the Cayley Partner, right? Okay, what else? Right. So using our parametrization, we also proved that, the following. There are no representations in these components which factor through a proper parabolic subgroup of GR, right? And here is, I say this phrase, this should imply that every representation in the components are positive. Now, the thing is that, okay, there is an extra condition that you can impose on positive representations. And this is, so it's being positive, right? Well, let me write it again. And then this extra condition that the representation does not factor through a parabolic, right? So how can I say that? Don't factor through parabolic. Okay. So what Guichard-Labourie and Wienhard tell us that they have been able to prove is that this is a closed condition. That if you add this condition, right, then this is a closed condition. Then that defines components. And with our methods, we have been able to show that, in fact, the representations do not factor through parabolic. So if the result is true, and they're telling us that it's true, and it's just they're writing up, then all our conjectures are true. In particular, the results that we found for SOPQ, the exotic components will be the higher Teichmuller components, right? So basically, the conjectural aspect of all this is just hanging of that thing, that proving that this is a closed condition, right? And so it seems that that is the case. Yeah, so I put it as a conjecture, but as I'm saying, yeah. So, okay, so these are the results, and we have any more results? Yeah, so the rest of the talk, I will just define the objects appearing in these theorems, right? And they're a bit technical. I try to, make it as mild as possible. And then to give an idea of this parametrization, this general Cayley correspondence, okay? So, but, yeah, any questions before I get into these definitions and so on? Okay, so let me get to the definition of magical nilpotent, right? Well, we find it's a very nice, interesting thing. So take a non-zero nilpotent element, right? And so this, remember, defines you SL2 a tedious triple. And so you have these relations here, right? So an SL2 inside G. G is complex, huh? And then you can consider two different decompositions of the Lie algebra, of the complex Lie algebra G. So one decomposition is as an SL2C module, right? So this is acting, of course, via the adjoint representation, and you can decompose it in terms of according to the SL2C modules, and every Wj is a direct sum of some copies of the, nj copies of the unique j plus 1 dimensional irreducible SL2 representation, okay? And in this decomposition, notice that W0 is a subalgebra of G. Okay? So this is the decomposition as an SL2Z module that you have. Once you have chosen the nilpotent, right, and the SL2C, you have this. But you have another decomposition, which is by taking the action of H here and the weight decomposition, right? The adjoint action of H in the direct sum of G, J's, right? Where this, the adjoint on Gj is actually acting by J, right? And so you have this decomposition, and of course you notice that the nilpotent element shifts Gj to Gj plus 2, and the other nilpotent sends you Gj to Gj minus 2. Okay, so this is the thing. Then you have the centralizer of the element E of the nilpotent element as this the kernel of this of the adjoint action of E, and this can be written as a direct sum of Vj's, right? And these Vj's are actually the intersection of the Wj with the Gj's, and these are the highest weight subspaces, yeah? And of course V0 is just W0. So this is just Lie theory representation of SL2 and so on. So you have these ingredients. So don't get discouraged. I mean, this is quite simple, I think. SL2 module decomposition. These are the decomposition, and from there you define these Vj's. Okay, so with these ingredients, so here's the fact: you can define a vector space involution determined by this nilpotent. This involution, so is a complex involution from G to G, which is defined on W0. You take just the identity, and on the Vj's, you define it on the, excuse me, not on the Vj's, but on the action of the different powers under F of Vj, and this actually covers the whole Lie algebra. You define it like this other thing, minus 1, k plus 1, so on. This is a vector space involution, right? So here's the definition of magical. The magical is that the nilpotent is magical if this is actually a Lie algebra involution. So this is always a vector, for any nilpotent is always a vector space involution. But if that involution happens to be a Lie algebra involution, then the magic happens, right? And when we were working on this problem, this was not our perspective, actually. We were working from another point of view, which is equivalent, about pre-homogeneous vector spaces. But the fact is that we came back to the paper of Hitchings on the symplectic case. And this is how he actually showed that a result that you can attribute to Constant, that every principal nilpotent is magical. So remember that in the nilpotent cone, there is an open orbit consisting of the open and dense orbit, the principal nilpotents. Those are always magical, right?
What is the pre-homogeneous spaces? Is the closure of this?
I can tell you, the pre-homogeneous spaces, the SL2s define also pre-homogeneous spaces, right? I'll tell you about that. I mean, there's a long story, actually, but that's how we got to this, right? And it was a more general kind of a story. And yeah, I'll tell you. It's quite nice actually. But at the end of the day, we were able to package that in this other purely theoretic way, and which was very similar to how Hitching actually was considering the nilpotent element, and he showed that this was a Lie algebra involution. He didn't call it magical because, because it was just a property that the principal nilpotent has, but this was his point of view, right? And so the fact is then that that E magical now, because it's an involution, it's a complex involution, then you can take the +1 eigenspace of sigma E, and you have H, and then you can take the -1, and this is M. And so this is the complexified Cartan involution. And as I was saying yesterday, Cartan knew about Higgs bundles. And here in the Higgs bundle picture, you see the description of real forms in terms of holomorphic involutions, right? But of course, attached to a holomorphic involution like this one, sigma E, now you can choose a conjugation, an anti-holomorphic involution defining a compact real form that commutes with it. Cartan proved that that exists. And then the composition of both, right, of this sigma E, so you can define a theta E, which is sigma E composed with this tau that defines the compact real form, commuting with sigma E, and this now is anti-holomorphic, and this defines you a real form, right? And so this is so now from, I don't write it here, but the way you get this real form is precisely by choosing this compact anti-holomorphic involution, right, and composing, and this is now an anti-holomorphic involution that defines you the GR. And this is the canonical, this is what we call the canonical real form associated to E, okay? And this only happens because this is a Lie algebra involution, right? So some examples of magical nilpotents. Of course, you always have, so this is an example of a principal thing. You can compute things and realize that the real form that you get is SL3R, right? And this magical nilpotent is actually a principal nilpotent, right? So we knew about those. I mean, Hitching knew about those, and Costant and other people. Yeah. But here is another example, which is also, I mean, okay, I want to anticipate things, but here is, you choose the complex symplectic algebra, SP2NC, and you choose this, nilpotent here. So this one, you can check, is also magical, and what you get here is actually you get the split real form, right? But this is not the principal. This is not the principal magical, right? What you get is actually, from the point of view of positivity, you get the notion of positivity that relates to the Shilov boundary. Okay, you get to a maximal parabolic, right? Not to the Borel. Okay. And indeed, the same nilpotent, you can regard it as an element in this complex Lie algebra. And also there, it leads to the real form, which is SUNN, which is, of course, is not a split, but is the Hermitian tube, right? So these are examples of magical nilpotents. So here are some facts. So if E is a magical nilpotent, then in the decomposition of phi, it so happens that only the odd representations of SL2C appear. There are no even dimensional. Only the odd representations appear, right? And now let me get to some stuff. This is a mechanism from which you remember in my Cayley correspondence, there were some numbers, mj, and there was this Cayley group, right? And so there is a Lie theoretic yoga that is a little bit technical, and I think that I will go quickly through it, that somehow you can extract these numbers, right? So there is some computations from which, let me just escape the details, you can extract these numbers, mj and the mc, that appeared in the Cayley correspondence, right? Perhaps a more interesting thing is to get to how you actually identify the Cayley group, right? And so the Cayley group is that we defined in the G0 part of the previous decomposition, right? We defined a Lie algebra involution, which is given like this, right? And then from there, okay, let me just, you can, in this complex Lie algebra, G0, you can identify a real Lie algebra, right? And again, because you have a holomorphic involution, you take the anti-holomorphic, the compact one, you can construct the real form. And there is a piece of the Lie algebra of the Cayley Partner is to take in this with this piece, and then you leave the rest out. And so this is the Cayley Partner. The Cayley Partner of GR is the group whose Lie algebra is this, and the maximal compact maximal compact group of GR with Lie. Yeah, this doesn't make much sense. And yeah, so yeah, the maximal with Lie algebra. Yeah, the maximal compact is the Lie algebra, is the maximal compact of this. Okay, so there's a certain yoga from which from the magical E, you extract all this information, these coefficients and this Cayley Partner, right? And so then now we are coming back to these objects, right? As I said before, actually, you have this was the how we identify these components with this moduli space here and these sections of powers of the canonical. And as I was saying before, each of these pieces can be identified actually with a moduli space for another group, which is actually R+, right? And so yeah, I think so let me just very quickly, because we're running out of time, tell you how you get this map very roughly, right? Now, to get this map, this parametrization, you consider a very canonical object, which is a PSL2R Higgs bundle, which is given by this SL2R Higgs bundle here. Yesterday we described SL2R Higgs bundles, and so you take this one. This is in the Teichmuller component, right? And then take ET to be the frame bundle corresponding to K, right? So you think of yeah. So it's a C star bundle. T is C star, and so then yeah. Let me just show this map here, right? That basically from this moduli space here, right, which is a Higgs bundle here, twisted by this power, and these various differentials of different orders, you can concoct an element which is in here, right, in a precise way. And there are very, I mean, one of the issues is to prove that really a stability in this thing corresponds to a stability, and the same for polystability and so on. And this would take us time to prove, and is injective and open and close and so on. And this is how we get the Cayley correspondence that generalizes all the Cayley correspondences that we have seen, and that gives you the general picture for any magical SL2, for any magical nilpotent, and then for the positive representations. Positive, perhaps, with this extra condition of not factoring through a parabolic. So these details of the general picture will come up very soon in our paper. So I think I stop here.